Hello, everyone. My name is Daniela Diego. I'm a senior robotics engineering student from Universidad de Guadalajara in Mexico. In this video, I'll walk you through the motivation, design, and performance of my summer research project, titled Origami-inspired anchoring mechanism for compact underwater vehicles in environmental monitoring. This was done under the mentorship of Dr. Melisa Orta Martinez and PhD student Nathan Zimmer. Let's start by talking about why this project matters. Coral reefs are among the most biodiverse ecosystems on Earth. They host around 25% of all marine species, yet, they're increasingly threatened by pollution, rising ocean temperatures, and destructive human activity. These ecosystems need continuous monitoring and protection, but reaching and operating in such delicate and complex environment remains a huge challenge for robotic systems. While there are several existing underwater anchoring systems, many of them are large, rigid, and not well suited for operation near fragile marine environments. They also tend to be heavy and mechanically complex, which makes them harder to deploy in shallow reefs or in swarm operations. That's where compact, soft, and adaptable underwater tools come in. Our approach is to design a compact, deployable, and waterproof anchoring system capable of anchoring without damaging sensitive structures like corals and performing useful tasks. Inspired by recent work in origami robotics and foldable structures, as you can see in the image, space applications are already happening. Nevertheless, there are limitations. These systems tend to be heavy and mechanically complex, like I said before, which make them harder to deploy in underwater ecosystems. And they are not optimized for compact integration with small scale autonomous vehicles. So, evidently, there is a need for smaller, softer anchoring systems that can operate efficiently in tight, sensitive underwater areas without causing big damage. This leads to the core contributions of this work. First, we designed a small submarine, designed for scalability and modular integrations, along with a waterproof deployable mechanism using a spool driven actuation system that contracts a soft origami structure, inspired by the Hanflex origami pattern. Second, we integrated torque springs to allow passive expansion, enabling repeatable cycles of deployment and retraction. And finally, we validated the system under both air and underwater conditions to assess its functionality and robustness. Let's now move on to the methods. The submersible chassis was designed in SolidWorks, allowing for easy adjustments and modular integration. Its compact structure balances strength, waterproofing, and scalability. The CAD model shows the main components, including the hull, the thruster layout, and the internal frame. The origami structure was modeled also in all SolidWorks, allowing scalable geometric control based on key inputs such as radius, fold number, and base segment length. The deployment mechanism is based on a foldable origami structure designed to expand radially and anchor within confined spaces. The entire mechanism was mounted on a cylindrical submersible housing. To ensure waterproofing, we used marine epoxy to seal all openings, paired with aluminum end caps, gaskets, and rubber washers. The whole assembly was submerged for extended periods and moved around to simulate real movement underwater. It remained completely sealed with no signs of leakage. The actuation was achieved with a waterproof servo motor attached to a PLA spool structure. This servo rotates to pull wax polyester threads connected to opposite flaps of the origami. The rotation contracts the structure in a clean and controlled manner, and the same motion, reverse, allows it to expand. The origami itself was 3D printed using flexible TPU, allowing it to fold without permanent deformation. However, to ensure full recovery of its expanded shape, I added torque springs between opposite foldings. These springs store energy during contraction and release it upon relaxation, assisting the structure in returning to its expanded state. This approach makes the system more passive and robust because no second actuator was needed. In terms of mechanical performance, the contraction force required in air was consistent at around 27 newtons and increased slightly in water to around 33 newtons due to the added resistance from the surrounding medium. The mechanism handled these loads well and showed no visible degradation over multiple cycles. The traction time in air averaged around 5 seconds, while underwater it increased slightly to about 5.45 seconds. Deployment was faster, around 3 to 4 seconds in air and about 4.2 seconds underwater. These values remain consistent across cycles thanks to control actuation parameters like voltage and thread length. In terms of structural change, the origami contracted from a diameter of 135 millimeters to 70 millimeters, achieving a 48.15% reduction in size. This compactness is crucial for operating in cluttered underwater environments, and the radial symmetry of the mechanism enables it to anchor evenly from all sides. Finally, the graph shows the comparison previously mentioned between air and water in deployment and retraction times, showing up the consistent timing with a standard deviation of zero point 0.2 seconds between cycles. Here, you can see the submersible during a waterproof and control test. We submerged it in a shallow pool and sent basic commands using a remote controller, moving forward, backward, and adjusting depth. This structure stayed completely sealed with no leaks, and all thrusters responded properly. This confirmed that the integration between the chassis and internal electronics worked as intended. Future work focuses on integrating functional payloads into the structure, such as microplastic filtration models. This would transform the mechanism from a structural tool into an active environmental agent, optimizing both the material selection and the spring configuration to improve durability and efficiency, and most importantly, scaling the system to operate at greater depths with higher pressure and more realistic underwater dynamics. This work was a great step forward in demonstrating the feasibility of compact, origami based anchoring mechanisms for underwater use. But there's still much more to explore, especially in terms of long term durability, autonomy, and real world deployment in marine ecosystems. I'd like to acknowledge my mentors, lab mates, and everyone who supported me throughout this research, including Universidad de Guadalajara and Carnegie Mellon University, especially the Robotics Institute for making this summer possible. I hope this work contributes to the development of softer and smarter tools for protecting our oceans. Thank you so much.